Um, all right, I hope my microphone is on. Yes, it's on. That's unusual.
Yeah, we can hear you.
So thank you very much, Sushanta. I appreciate the introduction and the opportunity to share with audience. I hope there's some from Win and hopefully from IQC and others. Some of our research, and I thought I will start with a bit of an introduction about our group and what we call QNC MB facility. So let's just okay. One thing I want to do is to is to get my laser pointer, okay, and voila. So the main piece of the equipment which we have in the lab, which is a foundation of most of the things which we do, is the molecular beam epitaxy system, and it's a Vico Gen 10. It's a 3-inch wafer capable, and so it's pretty good for pretty advanced device fabrication. We at this point have single growth reactor with arsenides and antimonides, 3-5 semiconductors, and automated wafer transfer. So we can run 24/7, which sometimes does actually come handy. So what are those 3-5 semiconductors, arsenides and antimonides? So today we will be really focusing on this narrow stretch of gallium aluminum arsenide quantum wells, so not even band gaps. We'll be working in the quantum confinement, in the potentials which are created by barriers and wells. But overall, this is the space which we can work with, meaning the energy gaps and the lattice constant. Okay, and maybe a couple of words on molecular beam epitaxy for those who are coming from different directions. We tend to say that this is the most advanced epitaxial technique, or crystal growth technique for that matter. Everything is happening at the ultra-high vacuum with pressures, base pressures at 10⁻⁻14 atmosphere. So it's kind of like inverse spaceship. We have ambient atmosphere outside and ultra-high vacuum inside, kind of like interstellar conditions. Everything is ultra-high vacuum, ultra clean, and we deliver those fluxes of targeted materials to the surface. And of course, we try to learn what those atoms will do. They are not always doing what one would expect. Okay, this is a bit of an illustration of where we fit in with our portfolio. So in red is kind of what we can address, at least where we can add on to what already exists, because what is showing in this table are well-established areas of high tech. Not many realize, but more than half of your smartphone nowadays is actually gas, all gas, so basically 3-5 compound, and those are grown mostly by molecular beam epitaxy, but huge systems in the fabs which are focused on the growth of those circuits. We are focusing mostly on quantum nano, okay, just to make it really clear. And I'm not going to be going through all those things discussing it. We will be focusing today on terahertz. So this is terahertz QCLs, which is standing for quantum cascade lasers, is one of the heroes of today's presentation. And this is a current portfolio of things which we are involved in. So in photonics, we have quite a few things going on in quantum nano, of course, quite a bit. And all of that is underpinned by the growth fundamental studies, where we try to move on with the technology, understanding what's happening on those surfaces. So today we will be focusing on the QCLs and terahertz intersubund polaritons, or at least directions towards them. And of course, all that has something to do with the interfaces which we are trying to master. So this is the topic towards room temperature compact sources of coherent terahertz radiation. So why terahertz? This is the well-beaten up slide, really, showing the so-called terahertz gap. And depending on where you look, some will say it's 1 to 10 terahertz, some 0.1 to 30 terahertz. This turned out to be the hardest one to make inexpensive, to make it commodity. Yes, the terahertz have been with us for a long time, but typically with very expensive setups, taking pretty much entire laboratory. So what we are trying to do is to make them accessible to many things which could benefit from terahertz, and there's a lot of technologies which would benefit from it. This is aged already, to 2007 review article from Nature Photonics by Tanouchi, widely cited. So his vision was up to 2015, and he listed a lot of applications for terahertz. He was right in some areas, but he was overly optimistic in some others. This is an interesting new review, or reasonably new review article on industrial applications of terahertz sensing. State of play, and what it shows is the evolution. The graph here is kind of evolution of emotions around terahertz. There was a big excitement about the terahertz, and this is going to solve all the problems of humanity. And the problems were creeping up, solutions were not coming forth, so the enthusiasm was dropping. This is about where the Tanouchi came up with his article, clearly trying to invigorate a community, but it took a bit of a dip before we went into this, what is called slope of enlightenment, and reached the plateau of productivity. So there's a lot of applications now which qualify in this technology readiness level right at the top, which are deployed right there in the production or environmental testing. And this is just a sampler of where terahertz technology is now being used. I encourage you to look it up in the paper here. References I add typically at the top or the bottom. Most of those which are listed in this paper are really about the time domain spectroscopy, which I am not going to be talking today about. We are focusing on terahertz quantum cascade lasers, mostly at this point. And we do have things to show for that in applications, not the mass deployment of that, but our lasers will be flying into space soon enough in this GUSTO ultra long duration balloon-borne terahertz observatory. And this is just to reassure you, we have our University of Waterloo crest here. Okay, and for those who are curious of what really are those terahertz QCLs doing there, they are serving as the local oscillators for the ultra-sensitive superconducting infrared detectors, so terahertz detectors, and they are pretty much at the heart of the entire mission. without them, the thing just wouldn't be doing what it's supposed to be doing. Okay, so this was like a quick introduction. So this is a presentation outline I would like to, at this point, give, which is the, talking about the essence. I will make a brief introduction to the terahertz QCL, so what those quantum cascade lasers really are, and show the latest results which are coming from our group, and then move on to the polariton lasers. So just a little bit of introduction about polariton lasers and concept, and then polariton lasers in terahertz concept, and I will add a few details on very novel technique which we managed to develop for this very application, and then say where we are with this polariton lasers, or at least where we're heading, and of course conclude and thank those who really did the work. Okay. So as you can imagine, I'm not going to be spending much time on each slide. So buckle up. I am not going to go super fast, but many of those slides are just a quick show. Okay. So quantum cascade lasers. The first idea was really proposed in 1972 by scientists Kazarinov and Suris, and it was just realizing that now at that time already it was possible to make quantum wells, so why don't we bias them and then have those electrons hopping and emitting the radiation. It took quite a bit of time, over 20 years, till the first quantum cascade laser was demonstrated. It was in mid-infrared, and Jerome Feist, now at ETH Zurich, was the first author of that paper. And the terahertz had to wait almost another 10 years before they showed up in 2002. So just a little bit of an illustration of this idea of the cascading and how this is supposed to give light. So this is my most advanced PowerPoint animation. I hope I will impress you with that one. Okay, so we have those electrons after biasing, the going through dropping, emitting the photon, and it was just like the simple idea. As it turns out, you cannot make a laser out of that LED, sure, but not the laser. There are issues which are related to negative differential resistance, which are not compatible with having this stuff as a laser. So the Kazarinov idea really didn't pan out. You need more complicated structures for that, and the community moved to something which is resembling, gas lasers even, okay, with the 3 levels where you have the depopulation of the, so lasing levels are 3, 2, and then you depopulate them very quickly using the LO phonons, which in 3-5 semiconductors are pretty active. So the problem here is that what I drawn here are not for optical transitions. There are no photons yet. It's just the electrons are dropping. And the problem is that spontaneous radiative lifetime is 12 microseconds at 1 terahertz. So this is one of the challenges in terahertz here. Typical non-radiative lifetime for this, this is this tau 32, is 1 picosecond. So it takes quite a bit of injection here to get the population inversion to the point where you start emitting the photons. But once you start doing it, things are really going very quickly, and the lasing is there, okay? The modeling, there's quite a few things. Of course, this is all quantum, so the most advanced modeling is done with non-equilibrium Green's function, and there you can see all the quantum things which come up related to tunneling, dephasing, piling up electrons before the barriers, and so on and so forth. The predictive power of those models is questionable at this point, but the good thing is at least they can typically explain experiments when they are done. So the issues with the terahertz quantum cascade lasers and in general, quantum cascade lasers are that even though you have this, simple two-dimensional kind of drawing on the piece of paper which shows the quantum states, you really have the free motion of electrons perpendicular to your page, and you deal with paraboloids here, which is the energy versus wave vector are in fact subbands, not just levels. So there's a lot of scattering events going on, and those are mostly detrimental. So with exception of the LO phonon, which is, well, it's also actually detrimental, but it does help to depopulate this lower level, okay? But it also kills the upper, as it turns out. So there's a lot of work we have been done in understanding. Jérôme Fays, the scientist who first demonstrated the neat infrared one, wrote a nice book a few years back, and I encourage you to read if you want to learn more about the theory. So going into the state of the art for terahertz QCLs, and I should say that we were lucky to contribute at a couple of points here in the history of this state of the art. The main thing, of course, is to maximize the working temperature. You don't want to have the laser working at those dilution fridges or even liquid nitrogen. You cannot move this around easily. So you want them at the very worst to have them working with thermoelectric coolers, just like telecom lasers, and better still, to have them working at room temperature. So that part is still away a bit, but this is just showing a bit of a history here. So this is the early, after first demonstration of QCL, there was very quick ramp up of activities in terahertz, and of course optimism was soaring, and the more optimistic researchers were predicting the room temperature operation, before 2007. Well, soon enough, though, it turned out that things were not as easy. Things kind of flattened up. And they really froze at 2012, 2011. And this is work which we have done. It was a collaborative work. At that time, I was at National Research Council. So the growth was done there. But the work was a collaboration with University of Waterloo. Diane Ban, professor here and also WIND member. His student was working with us at National Research Council, and we also were working with MIT at that time with Professor Ching Hu. So this was a joint success. We got to 200,000. The optimism, of course, picked up, but then there was nothing. Nobody was able to beat this record for 7 years. And so of course, those optimistic projections were quickly wiped out from the boards, and hard work was going around the world to advance it. Finally, in 2019, a little step was made by Jérôme Fays, the guy who first demonstrated QCL at ETH Zurich. He went from 200 hour record to 210. So it was already well publicized, but it prompted us, us meaning Ching Hu, our former collaborator from here, to focus and recover our leadership, because we are getting all the citations here, so it kind of was a pain to lose them now to Jérôme. we were really lucky very quickly. We demonstrated the 250 degrees operation of those terahertz quantum cascade lasers. And that was a big story in Nature Photonics and well publicized by all the magazines. And just a few months later, after we published that paper, we got up to 260. So this is where we are at this point. We are working towards room temperature, and I was hoping to have even some new result today, but not yet. Okay, so that's the brief story of how we are climbing towards the room temperature. However, single-stage thermoelectric cooler already enables the taking those things out of the lab, and so this is just a page from this Nature Photonic paper I mentioned, where we demonstrated the operation of those lasers at very respectable powers, and with just a single thermoelectric cooler, and with the double thermoelectric cooler, we can push it up into very good powers, which are compatible with imaging, even not just spectroscopy of a single line. Okay. So a bit of a couple of words of the molecular beam epitaxy and characterization. That's where our strength is. Of course, optimization of the growth conditions is the key. We have been in it for more than a decade, so it's 15 years we managed to cover quite a bit of ground there. The big graph on the right hand side, it shows those hero lasers and the 250K operating temperature, and those are the high resolution XRD scans, and those sharp peaks here are just signatures of our super lattice. You have, in order to get these lasers going, you need well over 200 repeats. Those are very thick structures. They grow almost 20 hours, and stability of the fluxes, all kinds of issues like synchronizing with rotation with monolayers, calibrating fluxes very tediously, fusion cell stability. Those are all key issues, including the MBE system cleanness, which we had to optimize and keep track of in order to get with this performance to where we are at this point. Yeah, I mentioned here shatter transients. I didn't mention that, but this is basically what you use in order to stop the beams from getting to the wafer from your fusion cells. You just close and open the shutter, which is shielding the beam. So this is the graph which I lifted from our collaborator, also Diane Ban, Professor Diane Ban here from his group. They have very extensive program on terahertz and quantum cascade laser collaborative with us, and this is the paper is a fairly recent paper showing the state of the art in the field when it comes to maximum operating temperature versus the frequency in terahertz. And you can see here that there seems to be a bit of a pyramid-like structure. And the reason for that is that on this site, we start to have problems with the population by this LO phonon, which we are using to quickly depopulate lower lasing levels. So this is really challenging part to cross in this material system. And this part, on the other hand, is just difficulties with injecting the carriers selectively to the upper lasing level. Those things are really, really very close together to have the light generated at terahertz. In fact, at our operating temperature, the spacing between those lasers levels is less than KT at those operating temperatures and quite a bit less. So that's very unusual for any lasers to work in those conditions. So this is the status for that. So where do we go from here? Reaching 300K operation, that's what we are working toward. But you can see here that we are probably going to have hard time quickly advance on the wings of this pyramid here. So, but hopefully in the next year, we are going to show lasers which are operating at room temperature. With coolers, of course, because they do heat up as you keep working them, but hopefully the actual operating temperature is not going to be far from room temperature. So that seems to be realistic, but only in this narrow frequency band. It may take another couple of decades. I don't know. There are some serious issues here, but here we have room for creativity, of course, to advance in the broader range into room temperature. So we do need some new ideas here. Okay. Now, in the meantime, it was before we reconnected back with MIT. With all the stagnation with the lasers at 200 degrees Kelvin, we were thinking, okay, maybe we can come up with another technique for lasers, and this is about the polariton lasers. So polariton lasers have been already demonstrated at mid-infrared and visible, but nothing in terahertz. So at least we had some ideas of how to go about that, and I will explain that as we keep going. So I will start with just a quick tutorial on the polariton lasing. I call it primer. So this is this one is on the exciton polariton. So it's not what we will be pursuing. We are pursuing the plasmon polariton. So what you need a cavity which can contain the photon, kind of try to trap it as much as it can. So that typically they have like a double Bragg reflectors here, and your cavity here with excitons which are being generated either optically or electrically. And when you have enough interaction between the exciton and polariton, and cavity photons, then they create another quasi-particle, which is polariton. And those are pretty decent quasi-particles, as it turns out. But the transition to create them, you can see, this is as a function of strength. So H omega is the strength of the interaction between the two. And the gammas are broadenings which are related to the limited lifetime of the photons and the excitons in this cavity. And so this ratio has to be larger than 1. And you can see that looks like almost like a phase transition, where from simple perturbance we are going into the so-called strong interaction. So your levels, which initially are degenerate, split up, and this is called Rabi splitting, and you generate the lower and upper polariton branch. So this is shown. I'm not going to maybe go into details of the second one here, but closer to the laser action, you need the dispersive cavity, which would have the minimum for the cavity mode at 0K, and you try to engineer everything that your exciton energy is cutting through this dispersion, and the interaction leads to creation of this lower polariton and upper polariton, and this is actually shown here on those graphs in the experimental electroluminescence intensity. So how do you make laser out of that? you generate those hot excitons initially at higher K, and then they relax. So the polaritons, once the lower polariton branch, they actually have bosonic character, and this is very important because you can condense them at the bottom of the lower energy. They can condense as quasi bosons, and the rate of this condensation, as it turns out, is proportional to how many already we have there, and then they decay and emit this coherent emission. So they work in a way like lasers, except rather than having upper and lower level and aiming at the population inversion, here we are condensing those bosonic particles and then annihilating them, and through this process we have the coherent photon emission. So how do we go with the terahertz about that? We need to get this light matter interaction to create and have it stronger than cavity losses and material losses. And the only way we can generate the transitions at this energy is in the quantum wells, in the conduction band. So that's what we're doing. So we're trying to get possibly stronger absorption and low losses in this system, and hopefully meet the conditions which are necessary to have this strong interaction and formation of those polaritons. So we're trying to generate this splitting into lower and upper polariton, just like I showed in the exciton polaritons. Now, people were trying to do that and demonstrated some of the polaritons at low temperatures in square quantum wells. However, the problem with the square quantum wells is that you cannot bring them up to room temperature. The levels are not equally spaced. You start to populate all of them, and you end up with washing out your entire oscillator strand and transition from one sharp line, which is needed for polariton at low temperature, into the many lines and many transitions, and in fact everything broadens and is no good. So takeaway message from this one: square quantum wells will do the polaritons, but only at low temperature. So we need to go into something else, and one candidate which looked particularly promising are parabolic quantum wells. As you may remember, in the parabolic potential, the energy levels are equally spaced, and this, of course, gives us the chance that as we increase the temperature, we are not going to see splitting of those transitions. They will just add up, and they do. Okay, so this is unified absorption. In fact, what we are seeing is the formation of the multi-subband polariton. All of them kind of get together. Okay, so in modeling, and I would like to credit right away Chris Damer, my graduate student who graduated last year, and already works at National Research Council as a research associate, and he modeled the system rather meticulously, starting from Schrödinger-Poisson, and with the help of our heavy-duty theoretician Wojtek Pasek, we were adding non-parabolicity corrections, and then going through already existing models of semi-classical quantum well plasmons, coming up with the so-called effective permittivity, which plugs into the electromagnetic solver, which gives a guide as to how to make the cavity now properly tuned to the transitions which we're trying to pursue. Now, the parabolic quantum wells is a big challenge. It has been a big challenge till till we started to work on that. They have been pursued typically with so-called digital grating, where you keep opening and closing shutters, putting a little bit of aluminum, a little bit of gallium. That creates a lot of interfaces, not very good scattering, not very accurate. So we needed a continuous smooth gradation parabolic quantum wells. And this is again, Chris, he came up with the way to do that, which I wouldn't say revolutionized molecular beam epitaxy, but I think this was one of the strongest contributions into the field for the last decade or two. So what we had to do is to find a way to rapidly vary the temperature of aluminum source. That was one of the best choices we had. And varies in such a way that as we keep growing, the structure with gallium always open, so going algas parabolic quantum wells, we would really trace the flux exactly how it should be for the resulting quantum wells to be parabolic. And he was a graduate from electrical and computer in computer engineering in Calgary, as it turns out. And he came up with this method, which is involving the transfer function used in the electromagnetics quite a lot, but never applied to thermal systems, which are thought to be pretty nonlinear. And this is really working well for linear systems. I'm not going to really struggle to make it super clear for you, but this is how he went about that. First, you have to understand all the dynamics of the cell. So you give it a very sort of rapid ramping, which is dropping the temperature as fast as you can. You're dialing basically, much lower temperature than steady, and then the same up. And that generates the dependence of the atomic flux, which is plotted here, which is in this sort of scale of effective temperature, not flux, but I'm not going to go into details of that. So this is basically the how the melt is responding. And we want to learn from that, and you can construct the transfer function using the Fourier transform of those experimental data, and then use that to generate any profile you want. So this is we find, after initially doing numerical calculations, we found that it's just as good. Well, we can, or even better, to approximate it with the analytical function, our transfer function. And the result is this is our desired. The black line is desired traces of temperature to get the parabolic potential. So this is the temperature of the cell, so that's why it doesn't look parabolic, but it will translate into parabolic potential. And the magenta, the line, is what you need to request from the cell to really get the right flux. So this is pretty wild, and you would never come up with that without this technique. And it turned out that with this technique, with a normal growth rate, and we have to grow like 50 plus of those quantum wells, so it would take forever if we were to grow really slowly and rely on our normal flux calibrations. So with the very respectable growth rate, it turns out that we were able to achieve extremely good reproducibility for those parabolic quantum wells with errors of the aluminum composition better than 0.2%. And this was a real breakthrough in the field. With that, we managed to demonstrate the plasmon transitions, which are extremely sharp and retain their sharpness pretty much to room temperature. So it shows here the line width in the percentage. So basically, it's a ratio of the line width to the energy of the transition. And in order to get strong interaction, which is what we need for polaritons, we need about 15% or better. And you can see that we are well into below 15% up to almost 200 degrees Kelvin, which was pretty stunning for everybody working in this field at that time. So this was published in 2020 in Physiograph Letters, and we basically took it from there, going towards more experiments and learning how to make those polaritons. So this is basically showing the things which are needed to get the polariton lasing with metal-metal cavity with the grating. So this is custom designed cavity here, and this is the reflectance from that at some angle here. And you can see that we, even at 300K, we do have some hints of this polariton forming. And this is the scans for different temperatures. And you can see that the Rabi splitting, which is what I think I have it here. Yeah, so this is basically what we were after, is retained definitely up to 200 degrees Kelvin. So this is really remarkable, and I think we can work with that towards the laser. Well, we do have a few challenges ahead of us. So this is basically the path. The part which is somewhat uncertain at this point, if we have the right scattering. With plasmons in those quantum wells, this is now being studied, so those studies will still need to be done. Then once we have we put optical cavity, and not unlike the one which was used for those experiments I showed, and then have the terahertz radiation coherent shooting up once it condenses at the k equals 0, and all going well, we can go for the electrical injection. There are challenges at every step, and it may take a while. So going to summary of where we are and what are the prospects. So for terahertz QCLs, we already have 260s, and we think, and this is deployable. I say deployable, meaning the devices, we're already thinking how to use them in real life for benefiting the humanity, so to speak. Okay, we may be able to reach the max of 300. We have the NSF ground to do that. The problem is that we are likely to reach it only this limited spectral range initially, and of course we are searching on how to beat the odds and broaden it. But I think the technology of the terahertz quantum cascade lasers is finally catching up to the point where we will join those applications which are now broadly deployed in many industries, and security and environmental protection and so on. When it comes to the polariton lasers, we did develop the new MBE growth technique, which allows to, with high precision, grow those arrays of parabolic quantum wells. The same technique can be used now to grow any arbitrary profiles of compositions, which opens up a lot of other possibilities. We believe the technique can be transferred to other material systems too. So the work is only starting really here. We got this strong coupling at like 200K for sure. We think we are on the right path to get this strong coupling at room temperature, and of course there's lots of challenges with the lasers. We don't have all the answers whether they will be possible, but the science behind is really really fascinating. So this is pretty much the summary. So still much more to be done, and of course we are looking forward to all that. So this brings me to the credits, and on our University of Waterloo site. First of all, I would like to credit Chris. This was pretty much part of his thesis, at least the polariton laser part, but he also contributed, and Alan did, to the Terahertz quantum cascade lasers, and Wojtek Pasek now in Brazil. He is a theoretician specializing in KP theory. Nayong Kim and her group had been doing some work in this area, helping us with the optical absorption done with photoluminescence excitation. I also would like to credit Diane Ban, my colleague, professor here, who has been in parallel pursuing the Terahertz quantum cascade lasers and a lot of modeling, and of course we learn in one environment here, and we have lots of very good publications with him also, but I didn't quote all of them here. Just the 200K laser I mentioned. On the site of MIT, we have Ching Hu, one of the pioneers of the Terahertz quantum cascade lasers, in particular those with so-called resonance injection, and his postdoc, well, now postdoc, but it was his doctoral thesis, Ali, who had done a lot of fabrication and testing of those lasers, and the French group from University of Paris, Saclay, who had been helping us with the fabrication and modeling of the polariton lasers, and Chris actually spent some time in Paris working with them and contributing quite a bit of his own modeling into that. So this is we are about to publish a few other papers on that, and I also would like to thank our group. This is the group at the time when most of the research was done. We already have Wojtek in Brazil, Ida did her PhD, she's at MIT now, and Chris is at National Research Council. Bogdan is still here with Professor Jonathan Bao, Hosung back to Korea, Hadia finishing her master's, and Peyton working, and Alan in my group as postdoctoral research associates. Okay, so this is the credits. Quite a lot of institutions I would like to acknowledge here, and transformative quantum technologies have been very helpful. The polariton laser part was done with the support of TQT, but also benefited the Terahertz quantum cascade lasers. And with that, I would like to thank for your attention and answer any questions if there are any. Thank you.
Terrific. Thank you, Zbig. Amazing presentation. Terahertz quantum cascade. Fascinating.
Thank you.
The audience also must be this. But as audience may be looking at some question, I'm wondering, since you have bridged nicely then with the molecular beam epitaxy, the nanoscale system with the quantum wells and so forth. So what is your take in terms of how you see this bridge between the quantum nano evolving over the years? You have some insight that would be helpful for the audience.
Well, I must say that when I joined University of Waterloo, it's going to be 10 years in July. I thought I was like the main nano scientist, and then I learned that really most of the nano is nowadays played by chemists and biologists, and so for me that was quite an exciting discovery. But of course, most of this stuff we do is nano. Some of the devices would probably qualify into micron scale, but definitely all the components of those devices are in nano. And quantum, of course, is a natural part of that. So we do have ongoing collaborations with the, like in this slide here, I was, am I showing this slide now in the kind of,
right now the slides are not there, is just blank slide.
Yeah, but this is not in the presentation mode, right? I'm just showing it hopefully in this working kind of layout. Right? But I think hopefully it's not big enough here, and it just shows that our lab does have a lot of things to offer for quantum, right? So not just nano. We are working actively towards topological quantum computers with Jonathan Bao and quantum dot qubits, cavity exciton polaritons. We are working with David Snoke from US, and we have NSF grant for that. And cavity exciton polaritons is something which is basically with him. The Terahertz stuff is with the friends. Okay, so still collaboration is going on, and I think there's room for expansion. So I think it's hopefully this comes with some funding. But the model which we have been pursuing is to invest from whatever funding we have into collaborations, trying something, and we find that typically we get results which then help to get funding from funding agencies. Which one example here is the Terahertz QCLs with MIT, where the results which we got bringing the temperature to 250 generated pretty generous NSF grant, where I'm also PI, which is kind of pretty unusual for NSF to have the foreign, even Canadian co-PIs. So yeah, that's
very exciting. Thanks. There is a question in the audience. Is there any band gap engineering could help to overcome the problem of gap approximate KT in quantum cascade lasers?
Hold on. I'm just maybe see if I can. Okay, I can see it. Okay, you're breaking up a little bit, Sushant.
Okay.
Okay, engineering could help to overcome the problems of gap approximately KT. Oh, well, yes, the creativity of researchers is endless. Let me see if I can bring this slide, which is just showing a bit of that here. I think this probably is the one. So you can see here those. Okay, can you see my cursor?
Yeah, we can see. Yeah.
Okay, so those two all of those triangles are Terahertz quantum cascade lasers, which were very different design, not a direct resonant injection into the upper lasing level, but injecting to another level, which is LO phonon above the upper level. So this suddenly creates a lot of space in very selective injection, and you can see that those points are quite a bit above this line, which is showing the problem of the KT and the also selectivity of injection issues. So the work is going on still. They didn't really resolve all the problems. Those things are, as I mentioned, we do have very powerful modeling tools, but there is a lot of complexity in operation of those structures. And so what happens there is that we model the stuff to explain the experiments which we have. Then we say, oh, well, we got all the parameters right. We now can use this model with those parameters to show us the way. And this is how we do things. We follow the theory to make the next step. Sure enough, next step doesn't end up anywhere close to what we are planning on. Okay, so we adjust the theory again, and so on and so forth. Little by little, we climb this ladder, and different ideas are appearing, and they can be tested theoretically. So those models are getting better and better. There's quite a few of them. There's a density matrix approximation, Monte Carlo combinations of those, the rate equations models, which take in parameters from other stuff, and the Diane Bahn's group is doing quite a lot of simulations on those things. So we are hopeful that we can beat that. Yeah.
I think it was quite fascinating. It's like seeing this kind of interesting, and people often, they are also using this as in terms of the fingerprint regimes, in terms of sensing significant way. So quantum cascade lasers. So is there any direction in your group also looking at these fingerprint regimes, sensors, quantum cascade?
So the presentation, I understand, is recorded. Yes. So I hope, and will be available on your website, the link. And I want to emphasize that we are open for business. Okay, that we do lots of research which is related to molecular beam epitaxy. We do have our projects which are device oriented, but we have the capabilities and room to take in your ideas and convert them into reality. So please check the presentation, in particular the kind of materials which we can do. Some of that will require a bit of a project. It's not like everything we can throw in and it will end up to be a record breaking. But initial tests we typically could try to smuggle in and help you on your way towards your Nobel Prize. Okay. So yeah.
Thank you so much, Zbig. Such a pleasure, and let's continue the dialogue and see how quantum and nano can be bridged further. Thank you.
And I appreciate the opportunity. So thank you very much.
It was a pleasure.
Okay.
It was a pleasure.
Bye.
Bye-bye. Take care. Bye.